In November 2023, a machine 15 billion miles away stopped making sense. For 46 years, it had been sending back pristine data from the deep dark of space. Then suddenly, nothing but an endless loop of binary gibberish. It was the farthest human-made object in existence, and its mind was failing. But the engineers back on Earth weren't ready to let it go. To understand how we fix a spacecraft that is currently flying through the interstellar medium, I need to take you back to 1964. Gary Flandreau was a graduate student working at the Jet Propulsion Laboratory. His job was to map out launch windows for the outer solar system. While crunching the numbers, he noticed a quirk in the orbital mechanics. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune were going to line up on one side of the Sun. It's a configuration that happens exactly once every 176 years. Flandreau realized that if you timed a launch perfectly, a single spacecraft could hop from one planet to the next. But getting there required a trick of physics called a gravity assist.
Think of a planet like a massive freight train moving in a wide circle around the Sun. If you throw a tennis ball at the back of that train, it bounces off. From the perspective of the train engineer, the ball approaches and leaves at the exact same speed. But from the perspective of someone standing still on the ground, or in this case, the Sun's frame of reference, something incredible happens. The ball steals a tiny fraction of the train's forward momentum. The train slows down by an unmeasurable fraction of a millimeter per century, but the ball is violently hurled forward. When Voyager 2 eventually approached Jupiter, it was traveling at roughly 10 kilometers per second. It dove into the planet's gravity well, stole a massive chunk of Jupiter's orbital momentum, and was slingshotted out at 25 kilometers per second. It didn't just fly by, it was physically dragged forward by the planet itself. But to survive a grand tour of the outer planets, the spacecraft had to be tough. We are talking about 1970s engineering. Across its 6 onboard computers, Voyager has a total of roughly 69 kilobytes of addressable memory. That is barely enough to hold a single low-resolution internet image. And yet, the architecture of that memory is a masterpiece of survival.
And because even that wasn't enough, the engineers split the memory into 2 types. For the core brain of the ship, they used plated wire memory. This stores digital bits as magnetic domains on a thin iron-nickel plated wire. Why use wire? Because Jupiter is surrounded by a brutal radiation environment that would instantly fry modern electronics. Plated wire memory is practically bulletproof. It's also non-volatile, meaning if the spacecraft loses power, the core programming doesn't get wiped out. But plated wire is slow, so to handle the rapid-fire data coming from the cameras, they needed something faster. So for the flight data system, they used CMOS RAM. It was one of the first times this technology was ever used in space. It was fast, but volatile. If the power dropped, the memory vanished. And because even that wasn't enough to hold all the data during a planetary flyby, they packed a physical 8-track magnetic tape recorder to spool the data until it could be beamed home. Of course, none of this works without power. Out past Mars, the Sun is just a bright star. Solar panels are entirely useless, so Voyager carries its own heat. It uses a radioisotope thermoelectric generator, or an RTG. It's essentially a nuclear battery with 0 moving parts. Inside, a lump of plutonium-238 naturally decays, throwing off intense heat. Surrounding this plutonium are thermocouples made of silicon germanium. One side of the thermocouple faces the hot plutonium. The other side faces the freezing vacuum of deep space. That extreme thermal cliff forces charge carriers within the metal to diffuse from the hot side to the cold side. It's called the Seebeck effect, and it turns raw heat, directly into a steady electrical current. In the late summer of 1977, Voyagers 1 and 2 left Earth. Despite launching a few weeks later, Voyager 1 was placed on a faster, shorter trajectory. By March of 1979, it reached Jupiter, discovering active volcanoes erupting on the moon Io. By November 1980, it reached Saturn. Here, the mission faced a critical choice. Scientists desperately wanted a close look at Saturn's largest moon, Titan, because they knew it had a thick atmosphere. But the geometry required to fly close to Titan meant Voyager 1 had to be slung upward, completely out of the flat plane of the solar system. By choosing Titan, they sacrificed Voyager 1's ability to visit any other planets. But that was the beauty of having two ships. Because Voyager 1 succeeded at Titan, Voyager 2 was allowed to continue on Flandreau's original Grand Tour. It flew past Uranus in 1986 and Neptune in 1989. To this day, it remains the only human-made object to ever visit those ice giants. By 1990, Voyager 1's Planetary mission was over. It was heading out into the dark. But Dr. Carl Sagan, a member of the imaging team, made one final request. He asked NASA to turn the spacecraft's cameras around and take one last picture of home. The result was the pale blue dot. From 3.7 billion miles away, Earth was caught in a scattered ray of sunlight, taking up less than a single pixel of the image. Sagan later wrote that every human being who ever was lived out their lives on a mote of dust suspended in a sunbeam. But how do we even receive a picture from that far away? Voyager's radio transmitter operates at roughly 23 watts. That is the power of the light bulb sitting inside your refrigerator. By the time that 23-watt signal travels billions of miles back to Earth, it is astonishingly weak. We receive it at roughly 10 billion times weaker than the signal required to run a standard Wi-Fi network. To hear this faint whisper, we rely on the Deep Space Network. These are massive 70-meter parabolic dishes located in California, Spain, and Australia. The receivers are cryogenically cooled to eliminate the thermal background noise of the metal itself. Engineers even link the dishes across the globe to create an artificial receiver the size of a continent. In August 2012, the data from Voyager 1 shifted. It had officially crossed the Heliopause. The Heliopause is the boundary where the solar wind, the constant stream of charged plasma blown out by our sun, loses its outward pressure and is overtaken by the interstellar medium. Voyager 1 had officially entered interstellar space. Now, you will often hear people say that Voyager has left the solar system, but astrophysically speaking, that isn't true. The true gravitational edge of our solar system is the Oort cloud, a massive spherical shell of icy debris. At its current speed of 38,000 miles per hour, Voyager 1 won't even reach the inner edge of the Oort cloud for another 300 years. It will take roughly 30,000 years to come out the other side. Which brings us back to November 2023, the gibberish. When Voyager 1 started transmitting that repeating 0101 pattern, engineers at JPL didn't panic. They sent a command to poke the flight data system, forcing it to transmit a full dump of its internal memory. Because the ship is over 15 billion miles away, it takes 22.5 hours for a signal to get there and another 22.5 hours for the answer to come back. When the memory dump finally arrived, they found the culprit. Exactly one CMOS memory chip had failed. It corrupted about 256 words of code, roughly 3% of the system's memory. You cannot send a mechanic 15 billion miles to swap a microchip. The fix had to be entirely software-based, but Voyager's memory is incredibly cramped. There was no single empty block large enough to hold the 256 words of relocated code. So, the engineers got creative. They manually chopped the corrupted code into tiny fragments. They mapped those fragments into empty slivers of remaining uncorrupted memory scattered throughout the system. Then they painstakingly rewrote the master program's jump instructions. They taught the 1970s computer to leap over the dead chip, find the hidden fragments of code, and execute them in the perfect sequence. On April 18, 2024, they beamed the patch across the solar system. 2 days later, the telemetry arrived. Voyager 1 was awake. It was making sense again.
The plutonium inside the RTGs is decaying. The thermocouples are degrading. Every year, Voyager loses a little more power. Engineers have been slowly turning off heaters and instruments to keep the core alive. But sometime in the late 2020s, there won't be enough juice left to run the transmitters. Voyager will finally go silent. But it will keep flying, carrying a golden phonograph record loaded with the sounds of Earth drifting through the interstellar medium for millions of years. It makes me wonder, if you could add just one sound or image to that golden record to represent humanity as we are today, what would it be? Let me know down in the comments. And if you want to keep exploring the mechanics of our universe with me, hit that like button and subscribe to LynxSifts. Think of it as our own gravity assist, transferring a little momentum to help propel this channel into the great unknown. I'll see you in the next one.